Okay, Geometry AB. Yesterday we finished up section 11.2, which was on the surface area of prisms and cylinders. And today we're moving on to 11.3, where we're going to talk about still surface area now, but moving on to two different shapes here, and that would be pyramids and cones. And really, before we do anything else, we should probably have a quick talk right here about what exactly a pyramid or a cone is. And a pyramid, we have drawn down here at the bottom of this slide right here, guys. When most of us hear the word pyramid, we kind of instinctively think of the pyramids out in Egypt. And that certainly is an example of what a pyramid can look like, but not every pyramid has to work that way. Okay, so the defining characteristics of a pyramid are going to be that there is going to be a polygon down here as the base of the figure. And like we talked about yesterday, base doesn't necessarily mean that it has to be on the bottom, but especially with a pyramid, it almost always is. So we've got a polygon on the base, and in this case, that's a square. And then, moving up from the sides of that square base, we have a whole bunch of triangles that then move on up to the top. So if we took a look at this figure right here, you can see that there's a triangle that I'm going to highlight in orange right here that goes from one side of the square base all the way up to this magic point up here on top, which we call the vertex of our pyramid. So again, that's the point that's usually on the top, although not always, but that's where we're at. And if you undo some of the mess that I made in this figure here already, you can realize here that there's going to be 4 of those triangles going around the side, and those are called the lateral faces. So when we look at a pyramid here, we can see that it's got one polygon down there on the bottom and then a certain number of triangles going around the side. So this one right here, everybody, is what we're going to call a square pyramid. And again, every pyramid is named, this one is a square pyramid, according to the shape of its base, and this one has a square down there on the bottom. Now, when we talk about the formula here for surface area of a pyramid, all right, this formula looks a little bit different than what we saw yesterday or 2 days ago. We start off with a capital B, and just like when we were talking about surface area of prisms, capital B stands for area of the base. Now, if you recall, though, from 11.2 notes, in a prism, there was a 2 in front of that B right there, because every prism had 2 bases. But every pyramid, as we look back at this figure down at the bottom, every pyramid only has 1 polygon base. There's not a congruent and parallel polygon on the other end of the figure the way there was in a prism. So that's why there's only 1 base, so it's only a 1 for the capital B. And then, for what we call the lateral area, that comes from this second term in the formula over here. So the area of all of those triangles added together can be computed pretty efficiently with the formula of 1/2 times P times this cursive L. And the P, just like it did in prisms, everybody, stands for the perimeter of the base. So for us, we would add up all the sides in that square on the bottom right there. And the cursive L is something new. The cursive L here stands for something called slant height. And when we talk about the height of a pyramid, that can get a little bit confusing. So if we take a look at this figure right over here, if you were to imagine yourself standing up here at the very top of one of those big pyramids in Egypt, and you wanted to get down onto the ground right there, there's really 3 different ways you could do it. All right. One of the ways would be to slide around one of these edges of the pyramid right over here on the side, where 2 of those triangular faces come together. That measurement right there in black is what's called a lateral edge. If you were to slide right down the middle of one of the triangular faces to end up right down here at the midpoint of one of the sides, that right there is what we call the slant height. It goes down the center of one of those triangles on the side. That's what we're going to be using today. And later on in this chapter, when we start talking about volume of a pyramid is going to use the concept that you could somehow drill or cut a hole right in the top of that pyramid and then maybe rappel right down there like Indiana Jones in Raiders of the Lost Ark and get right to the center of the base and actually be inside the pyramid. And if you were to do that, that is simply what's called the height of your pyramid. But today, we're looking at this concept right here, which is the slant height, which is going to go from the vertex of your pyramid right down here to the midpoint of one of the sides. So there's our formula, guys, for surface area of a pyramid. It's 1 base plus 1/2 times perimeter of the base times the slant height of the pyramid. So let's see it in action here, everybody. All right, so this first problem, let me move that for you right here, is going to look something like this. And just like the diagram that we just drew, we see a pyramid here with a single point up here on the top. We've got a square base down here on the bottom, and a bunch of triangles going around connecting all that. So like we've been doing, we're always going to start off with our formula here. That surface area of a pyramid is going to equal a capital B plus a 1/2 times perimeter of the base times the slant height. Step 2, as always, fill in what we know. All right, so the capital B right here stands for area of the base. And as we go and look at the base here, let's go ahead and highlight that in yellow here. The base is this square down here on the bottom of the figure, and each side of that square is going to be 18 centimeters long. So, showing a little work off to the side right here, capital B, which means area of our square base, is just going to be 18 times 18, which is going to get us 324 square centimeters for the area of that base. So capital B is going to be 324. That's the area of the bottom that's shaded in yellow, and now we're going to try to find the area of all 4 of those triangles together. So we're going to go with a 1/2. And then here we go. The first thing we have is capital P, which stands for the perimeter of the base. So let's do a little side work to figure out perimeter. Perimeter is the total distance around the outside of a polygon. So a square has 4 sides here. Each one of them is 18 centimeters. Now, when I ask people how would we find the perimeter of a square, the answer that I hear, that I don't like often, is that we would add all the sides together. And I'll watch high school students grab their calculators and type in 18 plus 18 plus 18 plus 18. It works, but it's a little juvenile. Guys, when you're adding 4 18s, you're really just taking the length of each side, which is 18, and multiplying that by the number of sides, which is 4, and that's going to get us 72 centimeters now for the perimeter of our base. All right, so that takes care of the capital P, and now the cursive L, everybody, that stands for slant height. And as you can see here, slant height was drawn for you in this diagram, and the slant height is right there in red. Now, the 41 that they gave us right here is not the slant height. The 41 is actually the length of what we call the lateral edge here. So, if I were to redraw some of this figure right here, let's take a look at what's going on here, guys. I'm only going to draw this triangle that I'm kind of shading right over here, and I'm going to draw it down here on the side. Let's see what it looks like. Kind of something like that. Now we have a right angle right here, so I'm going to put that right angle in the corner. We know that this piece right over here, which is 41 centimeters, that measurement is going to go right here. Here's where it gets interesting. This piece down here, the entire right edge right there on the bottom of that square pyramid, is 18 centimeters long. But one of the things that the slant height will do is it'll bisect this side right over here. So if an entire base edge right there is 18, this little piece right down here is only going to be 9 centimeters long. So what we're looking at here, everybody, and this happens a lot when we're dealing with pyramids here, is we're dealing with a right triangle where 2 sides of it are known. We've got a leg of 9 and a hypotenuse here of 41. So we could use the Pythagorean theorem now in order to figure out the length of L right here, the slant height. And we could set up something like 9 squared plus our L squared is going to equal 41 squared. And if we do the work on that, that one is going to work out to be exactly 40. That's actually a Pythagorean triple, everybody. So 40 is going to go right there for the length of our slant height. And now at this point, guys, I would grab my calculator. In fact, I'll do this with you right here. And I would just type all of this in. We've got a 324 plus a 1/2 multiplied by a 72, multiplied by a 40, and we're going to end up with a total surface area of 1,764. Units were in centimeters here. We're talking about area, so that's going to be square centimeters for the units right here for surface area. Okay, so that's an example there. Let's see if we can't knock out one more right here and take a look at this one. All right, plot thickens a little bit right here. We have ourselves a pyramid, but our base is not a square the way it was in the past. Now we're dealing with a triangle right there. So this one gets a little bit more interesting. All right, so let's start with our formula once again. Surface area of a pyramid is still going to be capital B plus a 1/2 times the perimeter of your base multiplied by your slant height. Step 2, let's fill in what we know. Surface area is, and right off the bat, we end up with something a little bit challenging right here. Our base is a triangle, and if we look at the tick marks here, here, and here, we can see that it's actually an equilateral triangle. So I'm going to draw that equilateral triangle up here on the top of this figure, just drawn from straight ahead, and each side of that equilateral triangle is going to have a length of 10. Now the formula we need is for area of a triangle is going to be 1/2 times its base times its height. Okay, so let's see what we can do here. This is going to be 1/2. The base of this triangle we can see right down here is going to be 10, but the height of that triangle is unknown, and that's going to take a little bit of work. So the height of that triangle is this little dotted line that I'm drawing right there. And if we remember some things about equilateral triangles, all of your angle measures there are 60 degrees. So with a 90 and a 60, this is a 30-degree angle here, and now we're going back to a 30, 60, 90 triangle, which we learned about in Chapter 8, and we saw again in Chapter 10 as we were dealing with the areas of regular polygons. So to work on this one here, everybody, what's going on is that this 10 down here on the bottom gets bisected by the height so that this piece right here becomes a 5. And if you recall, in a 30, 60, 90, to go from short leg to long leg, we multiply by the square root of 3, so you're going to get 5 root 3 for the height of that equilateral triangle. All right, so now let's finish up then the capital B, or excuse me, the area of the base right there. And what do we get? A 1/2 times 10 is 5, times a 5 root 3, 25 root 3 is the area of our base. And that, I think, was going to be the hardest part of this problem. So capital B was 25 root 3. And we're going to add to that now. Let's keep following the formula. 1/2. The capital P means perimeter of the base. 10 plus 10 plus 10 gives us a base perimeter of 30. And then for the slant height, all right, once again, that 13 right here represents a lateral edge, but what we're really looking at is L, the piece in red right here, that's the slant height. Same trick we did in the last one. If this whole bottom side is 10, this little piece right here is going to have a length of 5. And remembering our Pythagorean triples, if a leg is 5 and the hypotenuse is 13, we know that our slant height has to be 12, because 5, 12, 13 is the second of the Pythagorean triples we were supposed to deal with back in Chapter 8. Now, if you've forgotten your Pythagorean triples, that's okay. You can do this by doing the Pythagorean theorem. It's just going to take kind of a while. Okay, but this problem is pretty well ready to go here. So surface area is going to equal, and this 25 root 3 is kind of sticking out like a sore thumb. It doesn't combine with anything else in this expression. So I'm going to leave it as 25 root 3, and then over here, the 1/2 times the 12 is going to get us a 6. The 6 times the 30 is going to make 180. So this right here is an acceptable way to leave the answer in simplest form. It does not get any nicer than that. And if they asked for it rounded to the nearest 10th or 100th or whatever, you guys would simply dump that into your calculator, hit the approximately equals to button, and get that as a decimal. Okay, we're going to stop the video right here, and we'll come back and we'll finish it up with surface area of cones next time.